effects of the rigid body and the propellers. Explained how we did all that in the post. I'd refer you to that post from September 13th on MT wallets, and the end result of all that, oops, if you bear with me, is we got to a plant transfer function for the roll axis and the pitch axis if we assume we're starting from hover. So given that, how can we control it? How can we, in the presence of a disturbance, some buffeting, wind, how do we maintain hover with this platform, given that that's the plant transfer function? And remember, we can think of it as a seesaw where we're actually not moving the center of mass. We're just pinned here, and we're going to roll, or we're going to pitch. And we can design those loops independently, and right now we're ignoring yaw. Now, the reason that I wanted to simplify it first, before introducing those gyroscopic effects later in state space formulation, was to understand our sensitivity to the different parameters of the platform, the geometry, the motor characteristics, the moment of inertia of the motor, of the propeller, and how do these things interact to limit the bandwidth of the system. And what does that mean? It means that when our platform is hovering and subject to a disturbance, it needs to recover, right? So a gust of wind, it's got to recover, right? As an example. Now, its ability to do that, its time response to that disturbance, is another term for it would be the bandwidth in the frequency domain of the control system. And this simple model is going to show us what governs that limitation. And so here's our classical model in Maple, and I put in some parameters that you'll find in the other posts. Our estimate for a torque constant, back EMF in magnitude is the same, and remember that this is 1 over the advertised kV for this class of brushless DC motor. And so we've covered that in a previous post. I'm still sticking with my internal resistance of the motor of 1 ohm. These units are just stated this way because Maple crunches the units correctly if I do it this way. That's probably high, but I stick with 1. We can check that when we get the motors, perhaps. Remember our thrust factor and our drag factor. We really covered that in depth in an earlier post. The top power and the torque coefficients, remember we got those for that APC carbon fiber propeller. We went through how to derive the thrust factor and the drag factor from that, from those data. Thanks to the University of Illinois at Urbana-Champaign. That was a great exercise. The gearbox, we're driving the propellers directly from the motor, so we've got no gear ratio and no efficiency associated with that, or inefficiency, so unity on those terms. The body moment of inertia, they did a little simple dumbbell model. Grabbed some what I think looked like reasonable estimates for the mass of the motors and the propeller combinations. Put those out 10 centimeters, so kind of like a dumbbell. The massless rod and the end of that, we're going to have these propellers. So I modeled the body moment of inertia that way, roughly 10 centimeters from my little seesaw model, a motor, and that's our body moment of inertia for this roll axis, and then pitch would be the same, so we're just looking at the roll axis right now. Propeller moment of inertia, I just modeled it as a spinning rod. I don't know, I picked a couple of grams, what, 2 paper clips is 1 gram, right? These are light propellers, so I picked a couple of grams. I looked at these motors and just made some estimates. Given the mass of the motor, most of it's probably in this copper that's fixed in the stator. But nonetheless, yeah, so I took that the mass of the rotor was half of the total mass of these advertised mass, which is high, I'm quite sure, but in any event, that was a decent estimate. And the radius of the rotor, came up with a motor moment of inertia, and then I just looked to see, even though my assumptions are probably pretty loose, what dominates. Is it the motor or the propeller as far as moment of inertia? It actually looks like the propeller dominates, even given these assumptions, but nonetheless, not significantly so, by a factor of 2, as I assumed here. So I just take the total moment of inertia of the motor propeller combination as the sum, and so that's our J total. And we can remember that J total from way back, where we were also crunching through the gearbox, and if you remember that post where I was confused about the gear ratio cubed and some other things that I had to fight through. So here's our total moment of inertia referred to for the motor prop assembly as though it's referred to the motor shaft. Initial conditions, covered this in a recent post where we assumed this was our nominal propeller speed to maintain hover, 100 radians per second. Now here are our A terms and our B term from our motor prop speed differential equation. And if you recall, it was d omega dt equals minus A times omega plus B U of t, or V of t, our voltage input. And that's after we had simplified it. Remember, we simplified our linearized equation. We did the Taylor series, and then we had that pesky constant term C, and in a recent post I went through the process of how we eliminated that term. We actually adjusted this term and arrived at that linearized differential equation. So we've got our A term and our B term, and those are arrived at by the estimates and the constants and some estimates that we made up above here. And just out of curiosity, here's a ratio for the A term of this part of the A term, and you can, looks like the motor, the motor part of the A term and the drag part, and so coincidentally that motor term dominates the magnitude of that, and that'll be relevant here in a minute. Our transfer function from roll or pitch. Now this is from that last post. That was the conclusion of our last post that I just showed. We had that, call it our plant gain, K sub G, that's in the numerator, and then our transfer function is a double pole, so it's a classic double integrator control problem, and then another double pole at A. And this is the primary value of this simple classical design approach up front, because through this we can really appreciate what limits the response time of our plant. This problem brought me back to textbook problems that I didn't fully appreciate until today. Namely, this double integrator. Almost every control textbook has a satellite attitude control problem, and they use it throughout the text as an example system to control. You got a spacecraft, and it's let me grab a prop. Here, little Amazon Kindle charger. So we've got this capsule in space, ignoring my fingers. Just imagine that my fingers aren't there, and this capsule's in space, and it's got a little thruster here, Let's say it's got a thruster here. So it can actuate by firing those thrusters, right? Well, it's a double integrator, 1 over s squared. And every control book in the world says stabilize that plant. So you look at it, and it's got, it starts with, it's 180 degrees phase, so minus 180, so it's inherently unstable. And then you design a lead compensator, and you create a little phase bump at unity crossover, and hey, great, we stabilized the platform. But I remember scratching my head thinking, what? Where do I pick that unity crossover? Like, what crossover frequency, which is, you kind of think of it as the closed loop frequency response, the bandwidth of the system. It's related to that. It's fairly close. What where do I pick that? Is this a math problem? What is it? So in this case, it jumped out at me that our motor propeller introduced second pole pair here. The speed of those poles dictates the best we'll be able to do with our lead compensator. And what do I mean by that? Well, first off, when we plot the root locus of our open loop, of our plant transfer function, it's inherently unstable. We've got these double pole at 0, and they take off into the right half plane, so it's unstable. And we could plot the Bodie plot of that. We're starting at minus 180, and that's our phase, and down from there. So these are both telling us the same thing. We got to do something here, right? So it's unstable. We need a lead compensator. So in PID terms, this is PD. So PID, proportional, integral, derivative. We got all the integral we need here. We need P and D. Really, we need the D first, is what we're going to design. Is we're going to put in a 0, the D, to stabilize this platform. So to get started, when I look at this, I realize that, well, okay, we have that double A pole is out here at roughly 40, right? 40 radians per second. A lead compensator is just going to buy us, I don't know, 30 degrees of phase, let's say somewhere. We're putting in a hump. But this is falling precipitously. So no matter what we do with the lead compensator, the double pole at A is going to pull us down anyway. So I just scale my lead 0 off of the A term. And then subsequently you cancel that 0 with a pole further out in frequency, and you get a root locus that looks like this. And so what you see here is our double pole at A is still here. We still have the double pole at 0. We introduced a 0 down here and a pole over here. Now this pole is kind of insignificant. Just has to be over here. And in pictures, if we look at a textbook, we can see what we've accomplished. That we're going to pick a gain such that this what a root locus is plotting is the poles as a function of gain. And so at a gain of 0, as we increase the gain, these poles are moving. This pole is moving this way. This pole is moving this way. This one's moving towards the 0. There's another one from here moving this way. Boom, boom. And then they break off this way. But again, these faster dynamics are relatively insignificant. And if we were to zoom in this region and look at a controls textbook, even for a second order plant, we would know that a pole around here is going to give us a natural frequency that is a function of that magnet that is given to us by the magnitude to the pole location, and the phase margin is going to be a function of this angle. And so we're seeing what we would expect, that okay, we're going to need a gain in here, and then we're going to have a stable system. Poles in the left hand plane. And the Bode plot tells us the same thing. Well, it gives us another view of it. In the Bode plot, we see, oh, okay, so we start at minus 180. Now we're getting phase, what's this, 30 to 40 degrees of phase margin. I'd have to look back at some design rules, but that's about right. Maybe even in the 20s. And in the end, there's going to be some uncertainty here because our plant model isn't really going to match. That's one of the purposes of this design process, is we're trying to account for uncertainties even in the plant. So our gain estimates aren't going to be perfect. So we want enough phase margin both to correct for what we know and also accommodate what we don't know about some of these terms and still have a stable system. So this picture tells us that, okay, we're going to want to pick unity gain. So we need 75 dB of gain because we're at minus 75. So we need about 75 dB of gain in order to have unity gain crossover where this peak is, and that happens to be at 10 radians per second as a crossover frequency. And so whatever that 75 dB of gain is, if we refer to our textbook, we'll see that it's going to put these poles right in here somewhere. That pole pair is going to be there because our sketching rules will reveal that we have about 30 to 40 degrees of phase margin, and the magnitude there will come out to be about 10 radians per second for a crossover frequency. So that's how we can look at it, either in the root locus plot or on a Bode plot. And an old teacher of mine said, well, any monkey can use MATLAB. You should be able to sketch these things. He's right. You'd have to be a pretty smart monkey to use these tools. Maple is pretty cool. I haven't actually used it much until now, and I really like it for this sort of thing. But we could have sketched, our plant Bode plot straight away if we were given this. We'd know we have a double pole at 0, and we've got a break frequency at A, or so we'd come down at minus 40 dB per decade, and then we'd break at around 40, which was where A was, and then we'd be going down at minus 80, and we'd have known if we had two poles coming here at low frequency, we'd start at minus 180, and then we'd break again, another minus 180. So yeah, we could sketch that. Root locus is a little more tedious to sketch. We could have obviously thrown our poles on there, no problem. You can sketch the asymptotes and then proceed to sketch the loci, but at that point, you could just call yourself a monkey and grab your math software and do it this way. So it's good to have sketching rules. It's good to generally know what you're trying to do, but these tools are really powerful and they speed things up quite a bit. Okay, so here's what jumped out at me in this, and why this is a good place to start with this simplified model. We can see that the placement of that lead, whether my scale factors are perfect or not, it's the intent and the limit are clear. We are governed by the speed of that double pole. at A, and that is driven by that is a result of the motor dynamics and the total moment of inertia, and that makes sense. Think about it. If we have a lot of torque and a light prop, a low moment of inertia for the prop, a small diameter prop, a lightweight prop, a lightweight motor, we're going to be more, that actuator is more responsive. So when our platform gets hit by a little wind, we spin the prop up and we can correct, right? Pardon my sound effects. As an aircraft gets bigger, like the Marine's Osprey or something like that, clearly that gas turbine running that big prop has a slower response time. So the bandwidth of that platform is considerably lower than our quadcopter. But we know that with mechanical systems in general, that the bigger they get, the lower their frequency response, the larger their the moments of inertia are, and the lower frequency responses they're going to have, both to disturbances and to actuation. So if we just look at A, and we don't look at this ratio here, which is means a little bit more to us now, it says that, well, okay, this first term in A dominates the second term related to the drag. They both have moment of inertia in the denominator. That sort of cancels out. Let's just look at this term right here. What it says is, as our load goes up, that would be electrical load and this resistance, and the moment of inertia referred to the motor shaft. As that goes up, A goes down. As A goes down, this is going to move this way. That's going to move this precipitous decline in phase down in frequency, which is going to limit where we can put our lead, and that's going to slow down. That's going to force us to put this phase hump lower in frequency. We're going to have a lower crossover frequency, a lower bandwidth of the system. So that's it. That is the rationale. It may not be precisely where we pick the lead, pole, and zero, and we may learn when we get to mess around with our test stand. We'll make some adjustments. But in theory, this is the method that we would employ to design a lead compensator for this double integrator plant, with another double integrator introduced by the motor propeller.